transformer relies on two key physics principles, electromagnetism and electromagnetic induction. Electromagnetism is when an electrical current generates a magnetic field. Electromagnetic induction is where a magnetic field causes an electrical current to flow. As you can see, one is just the reverse of the other. The basic transformer construction consists of a primary coil magnetically linked via an iron core to a secondary coil. The primary coil generates a magnetic field, and the secondary coil converts that magnetic field back into a flow of current or a voltage. So if we look at what goes on in a wire when we pass a current through it. When we pass a current through a wire, the red arrows representing the increase in current flow, a magnetic field is formed. To get a stronger magnetic field, we get more current to flow through the wire. Alternatively, what we can do is use two wires. Doubling the wires effectively doubles the current flow past a certain point, and therefore it doubles the magnetic field strength. We can use this in a transformer to make some very strong magnetic fields by using a coil. We can use this principle of multiple wires to greatly increase the strength of an electromagnet. By looping a wire into a coil, the same current carrying conductor passes the same point repeatedly. The magnetic field from each wire effectively adds together and makes for a very strong magnet. So if we look at what goes on in a transformer core, if we start with our coil of wire, if we now take a cross section through the coil and only consider the wires going into and out of the screen. By convention, we represent objects going into and out of the page using dots and crosses. And imagine an arrow being fired from a bow. If you can see the cross of the feathers of an arrow, it's travelling away from you. If you can see the point of the arrow, it's heading towards you. We can now add the magnetic field of each conductor as we have seen previously. The magnetic fields actually add together, creating one larger magnetic field. And we can represent this with field lines showing the combined or the resultant magnetic field. What we can then do is wrap this coil around an iron core instead, or a loop of iron. Now when we do this, because magnetism passes through iron much better than it does through air, we actually find that the magnetic field is constrained within the iron core. It permeates the iron core. Permeates just means travels through, basically. Iron can be several thousand times better at conducting a magnetic field than air. So if we now look at the primary side of the transformer, we can see how we generate this magnetic field which passes through the secondary coil. And what we'll now look at is induction in the secondary coil. The principle of induction involves moving a magnetic field past a conductor. In this view, as we move the magnet through the wire, some electrons move. We move the magnet the other way, and the electrons move in the opposite direction. The key thing is, if I move the magnet faster, more electrons move. So the faster I move the magnet, the greater the current flow. But key to this is that it's a moving magnetic field that causes the electrons to move. In other words, a changing magnetic field generates a current. So let's have a look at that inside the transformer. First, looking at the primary side of the coil, the red arrows represent the magnitude of the current, so bigger arrows, bigger current. I increase the voltage, the current increases, and I get a growing magnetic field. But once the current is the same, the magnetic field is static, it stays the same. So let's look at that again. Increase in voltage, increase in current, changing magnetic field. Voltage stays the same, current stays the same, magnetic field stays the same. The key thing is, a voltage is only induced in the secondary coil when the magnetic field is changing. So as long as the magnetic field is changing, we've got a voltage in the secondary coil. But once the magnetic field stays the same, there's no voltage induced. So just watch that again. Changing magnetic field, we have a voltage in the secondary, but when there's no change in magnetic field, we have no voltage. So what we actually need is an input voltage that changes constantly. And we can do this using a sine wave. As you can see, the sine wave constantly changes voltage, which constantly causes a change in magnetic field, which means we're always going to have a voltage induced on the secondary. So we now have seen how a voltage and a current flow can be induced in the secondary. The induced voltage depends on the strength of the magnetic field and the number of turns on the secondary coil. More turns on the secondary will generate a larger voltage. The strength of the magnetic field, though, depends upon the number of turns on the primary. So the voltage output of a transformer depends on the relationship between the number of turns on the primary and the number of turns on the secondary. So let's now have a look at that relationship. This is the transformer formula, and it's one that you need to know. It simply tells us that if we take the ratio of the voltages, secondary divided by primary, it's the same as the ratio of the turns, secondary divided by primary. Easiest way is to go through some examples. If we take 10 turns on the primary and 10 turns on the secondary, we look at the ratio, secondary divided by primary, and it's 1. 10 divided by 10 is 1. If we put that into our formula, and then rearrange the formula, what we know is that the output voltage on the secondary is 1 times the voltage on the primary, or that actually both voltages are equal. So equal number of turns, equal voltages. 240 volts in would give us 240 volts out. 10 volts in would give us 10 volts out. If we look at a different example where we have 10 turns and 5 turns, we now have less turns on the secondary. If we take the ratio of that, 5 divided by 10 is 0.5. We put that into our formula, rearrange it, and this tells us that the voltage on the secondary, the output, is half of the voltage on the primary. In other words, the voltage has stepped down. It's a step down transformer. We have half the turns on the secondary, so we have half the voltage on the secondary. You can probably guess what happens when it's the other way around. Again, work out the ratio, put it in our formula, rearrange the formula, and this now tells us that when we have twice as many turns on the secondary, we get twice the voltage on the secondary. This is called a step-up transformer. So in summary, voltage causes electrons to flow. Flow of electrons is a current. The current generates a magnetic field. By looping the wire, we can increase the strength of the magnetic field. The magnetic field passes easily through iron, and changing magnetic field induces a current in a conductor. Therefore, transformers have to use alternating currents. They will not work if you just connect them to a battery. The output voltage is equal to the ratio of the number of turns multiplied by the input voltage, or in other words, the ratio of the primary and secondary voltages is the same as the ratio of the primary and secondary coils.
During the last 10 years alone, the companies that together make up ABB Power Transformers have supplied over 25,000 transformers worldwide. Each has been designed and built to meet the individual customer's exact needs. And it is this experienced attention to detail that lies behind ABB Power Transformers' worldwide success. It is, in fact, the little things that make us big. And this approach is carried throughout our manufacturing process. Listening to our customers' individual needs, ABB's highly qualified designers evaluate the relevant data and generate transformer designs and design comparisons. For every new transformer, we can draw on our computerized records of thousands of installations. The results are tailor-made designs to meet the individual customer's exact needs. At the heart of the transformer designs, both from an electrical and mechanical point of view, is the core made up of steel laminations. For these laminations, ABB uses a wide range of high-quality steel grades. This enables us to choose the exact grade suited to each customer's individual needs. Our computerized cutting of these steel sheets ensures the highest levels of precision. Indeed, care and precision are vital throughout this stage of construction, since the core is critical in determining such factors as iron losses, vibration, sound levels and thermal stability. That's why so much care is also taken when stacking the laminations. Expert workmanship ensures that the core's electromagnetic properties are not impaired. The core will later be assembled with the windings to form the transformer's active part. The construction of the windings illustrates once again ABB's attention to detail and quality, as well as the flexibility of our manufacturing operations. high-quality insulated electrolytic copper conductors wrapped in special insulating paper are used for the windings. The exact choice of conductor and winding configuration is made on the basis of ABB's vast wealth of experience. It takes into account an array of factors, such as economy and loss expectation, as well as dielectric and mechanical stress. The work is carried out in an environment where every precaution has been taken to avoid any kind of contamination. And thanks to our highly trained staff and advanced manufacturing facilities, this critical and intricate stage of construction is carried out to the highest standards with both speed and cost efficiency. Once the windings have been completed, the first of two main drying processes is carried out. ABB places great importance on these drying operations since excessive moisture in the active part can jeopardize transformer performance. Moisture degrades, for example, the dielectric strength of the main insulation system. The first drying process is performed on the complete winding without core. After assembling with the core, the entire active part is moved into a vapor phase drying chamber. Additional drying operations can be performed by ABB to meet any special customer requirements. Tank design is affected by many variables. These include non-technical factors such as the method of transportation, as well as, for example, the type of overhead connections or type of cooling system. ABB has the experience and manufacturing facilities to meet all these variations. Where it is more practical or cost-effective, the work is subcontracted out. In either case, the design is always ours, production is closely overseen by us, and our stringent standards of excellence are always observed. To ensure the highest quality, regular tests verify the welder's workmanship on stress-resistant welds, which are vital to a transformer's construction. The welds themselves are also typically subjected to penetration, X-ray or ultrasonic spot checks. All the people involved in the work with an ABB transformer, starting from design, exercise responsibility for their individual contributions. This dedication to quality is one of the principal reasons why customers come to ABB in the first place. They expect the best. All our manufacturing operations are on target to meet the requirements of ISO 9001, and all are underpinned by a rigorous quality assurance program within the ABB group. Every operation, right down to the smallest detail, is signed off on a quality assurance record card by the person doing that job. In ABB's 24 factories worldwide, the assembly area is where the detailed care, skill and experience going into the various parts of an ABB transformer all come together for the first time. In this assembly area, where special standards of cleanliness apply, the assembly process is accompanied by the assembling of all the quality assurance cards to provide a detailed record of the transformer's construction. The proven technology of our comprehensive range of parts and accessories means an ABB transformer can have ABB quality built in throughout. At the same time, our flexible manufacturing operations mean that we can accommodate whatever specific accessories customers require, such as cooling systems, fans, control systems, various indicators, on-load tap changers, and bushings. The list goes on. After oil filling, the transformer is now ready for testing. A typical test sequence starts with lightning and switching impulse tests. After that comes an exhaustive range of other possible tests such as induced overvoltage and short circuit tests. All the accessories are also tested. In short, on every ABB transformer, we carry out whatever tests are required to ensure not only that the transformer meets the customer's demands, but that it has been designed and constructed to withstand conditions far beyond those it will ever face in actual operation. The transformer is now ready to leave the factory. The impact recorder placed on the transformer at the factory verifies that no disturbances take place during the transportation to site. Moving an object the size and weight of a transformer is no easy task, but ABB has unparalleled experience of delivering transformers to all corners of the world. By road, rail, ship, barge, and when time is of the essence, even air freight. When on-site tests and all other procedures have been carried out to ensure a long and trouble-free life, the ABB transformer is finally handed over to the customer. ABB's local presence worldwide has many continuing advantages for the customer. Within 24 hours, for example, we can have a representative on site anywhere in the world. Spare parts can be ordered for immediate delivery from any of our subsidiaries or ABB service offices throughout the world. Preventive maintenance is readily available, and our local offices will keep you in touch with worldwide advances in techniques and technology developed by ABB Power Transformers. In short, we are committed to keeping each ABB transformer running smoothly and efficiently wherever it is installed in the world.
Constructing a transformer. The transformer is an electrical component designed to change the level of voltage and current according to need. Operation. Electronic devices used to operate at different voltage levels delivered by the public. To operate these devices require a transformer. A transformer consists of a core of laminated silicon iron on which is wrapped a coil of insulated copper wire called magnetic wire. The first coil receives power from the grid. This coil generates a magnetic field which induces a motion of electrons in the second coil, producing a different voltage and current at the output. The difference of turns of wire between the primary and the secondary coil creates a proportional difference between the input voltage and output voltage of the transformer. The processor that we will build in this case is 18 to 18 volts AC, ideal for the amplifier of 300 watts. We teach to build it on our website, construyasuvideorecola.com. Materials: double-layer magnet wire. Copper wire is coated with the electric varnish used in the manufacture of generators, alternators, coils, electric motors, power transformers, etc. Silicon iron sheets. These silicon iron sheets come in the shape of the letter I and the letter E in their per sheet, forming the core of the transformer. Wax paper or press board. This roll is used to isolate the windings or coils of wire together. It has a paraffin bed which makes it flexible and ductile. It also seals out moisture and gives heat resistance, preventing from crystallizing. Masking tape. It is used to hold paper and wire between the windings. Foot screws and squares. The screws used to tighten the plates of iron, and squares or brackets are used to adjust the transformer to the chassis or cabinet. Formwork. Square one reel is used as support for winding the wire and prevent spreading, helping the smooth narrow of the wire. The formwork are available in various materials such as plastic, cardboard, and fiberglass. The Geometr Jaime Rios 7 planes design formwork, which may be downloaded from our website and then build them in straw or cardboard. It must make the pieces of cardboard gluing with the glue for wood, reinforcing with masking tape and coat of varnish which protects the reel from moisture, giving it consistency and durability. Calculation of transformers. Before the construction of a transformer, you should study our article on how to calculate a transformer. To calculate the number of turns of wire, we take the core area as the product of multiplying side by side of the mold. In this case, we have a formwork of 5 by 3.8 inches, which gives us a core with an area of 19 square centimeters. We take the constant 42 and divide it by 19 for 2.21 turns per bolt. As on the public of our country, we have a voltage of 115 volts multiplied by the number of turns per bolt. Now we know how many laps given in the primary winding. For the secondary winding, in this case 18 volts, multiplied by the number of turns per bolt, and 40 turns of wire get doubles. Construction. We drill the mold where you will enter one end of the primary winding wire. Setting the magnet wire. We removed about 5 mm rubber coating. Pre-tying the type of cable, joining welding, soldering iron and workpiece at the same time. It is necessary to sand a few millimeters from the top of the tip of the wire to remove the varnish layer, the electric isolation from the electric and moisture. Pre-tying wire tip copper. We connected the wire and cable, melting the solder with the soldering iron. Used thermal shrinking isolator 3 mm to isolate the joint. This heat thermal shrinking isolator isolate and taking the form of what it covers. Insert the wire through the hole. The wire is secure considering leaving the union within the mold. Secure the wire with masking tape. Winding the wire. Wrap the wire of the primary winding from bottom to top, from left to right, pressing well and taking care not to ride around on another and no spaces between the turns of wire. This is done in an orderly and neat to fit all necessary turns. We recommend that every 100 turns of wire, stick a piece of tape with the number of revolution and sew. If you lose track of laps, only to be returned to the last tape recorder and number of turns. When you finish all the laps winding the primary winding, cut the wire. We remove the dielectric varnish using a piece of sandpaper. We took a piece of wire and 5 mm retired covering coating. Thin the tip of the cable. Thin the tip of the wire. And join the cable and wire with the soldering iron. We cover the union with thermal shrinking isolator spaghetti 3 mm and apply heat. Insert the cord into an outlet slot. Isolating the primary winding. The primary and the secondary windings are isolated from each other with masking tape and waste paper or pressboard. The wax paper should cover the entire wire and secure with masking tape. Then, the paper is covered with more tape. Make sure there are no spaces through which they can touch the primary with the secondary winding. Ensuring the secondary winding. To wind the secondary winding, as in this case is a central tap transformer, wire is wound twice. Secure with tape masking and roll from left to right, pressing well and taking care not to ride around on another and no spaces between the turns of wire. At the end of winding, cut the wire and insert the tips of the tail end of the wire in the output slots. We sand the ends of the wire to remove the dielectric isolating layer of varnish. Detecting the central tap of the transformer center point. We must identify the ends of the windings measured continually with a multimeter. It is necessary to join leading edge of a winding with the tail of another winding. The starting point of a secondary winding must together with the tip end of the other secondary winding, thus forming the central tap. In order to weld the central tap point or center, remember to sand the pieces of wire so that there is adhesion of the solder and good driving. Recheck in continuity with the multimeter, which has a conduction between the three tips of the secondary winding. It is very important to be sure to correct binding center point. For this we must remove the two wires and remeasure. There should be continuity between the two wires. Again, covering with masking tape and wash paper. The secondary winding must be completely covered. The additional winding is 12 volts. To find the turns of wire, 12 volts multiplied by the number of turns per volt. The result is 27 laps for the additional winding. This winding fits a preamplifier which will complement the saving amplifier put another transformer. Like the previous windings, it's necessary to weld a wire to copper wire and masking tape on to roll the additional winding. Wire is wound down up to adjust the point of beginning with the turns of wire